Hello, everyone. So I want to take you on a little bit of a journey. The point of this presentation is to make a plea for a better understanding and use of geography in digital twins, and especially in interconnected digital twins. And I went on a little journey. I'm going to take you on some of that. I've been working in the field of geography, we call it geographic information systems, for about 30 years. And I didn't know I was doing digital twins. Basically, there's a strong case to be made that a paper map is an analog twin of the world. It helps us understand the world and plan around it and so on. So I went, this is relatively embarrassingly recently, I realized I was working on digital twins. And the start, I know it's the wrong audience to go to the basic definition, but a digital twin, virtual representation of a system used to model its behavior, and it helps us model, manage, optimize, and so on the system. That is what a digital twin is. It turns out that's also the description of many mapping systems. One thing I found very, very useful in my own understanding is the idea of maturity levels. We used to present in the geographic community, we would sit there and say, here is a point cloud that we've just captured from a drone of a building site, and it's a digital twin. And all the digital twin experts in the room would flinch because it isn't. But the concept of the maturity of these things really helped me understand what we do. And there's many different maturity levels, like Building Smart and IEEE. And at ESRI UK, we came up with one to help ourselves understand the nature of the systems we work with and their relative levels of maturity. So for example, I'm just going to run through this quickly. Level 0 is just a capture. If I take a picture of this room, I just have an image. It is a form of a twin in that I can use it to understand how the room was laid out and the people in it and so on. Raw capture can just be used for certain use cases. That helps us understand what we do in the world of mapping. Like just a satellite image or a point cloud can tell us a lot. You move on from that and you get visual twins, which is where you get photorealistic representations in 3D. And they can be used for things like, I'm working on a building site and there's raw materials here. What is the volume of that pile? How do I manage logistics across it? We then move into analytical twins, which is where you take geographic information and you run analysis against it and learn things from that analysis. Move on, we get to level 3, real-time systems, where you take the sensors that tell you about the flow of people along streets or electrical networks and loading or water networks, and you use them to bring that data to life and to model and monitor the system. Then we start moving into semi-autonomous things, and Credo, I think, is something that is like a semi-autonomous system. It's moving to a point where it can help make the decisions for you and maybe make some decisions. And then finally, and hopefully not today, we get to autonomous systems, where the system doesn't need us. It runs itself. It makes its own decisions. It becomes the system. This is going to need an amalgamation of AI and so on. But I found this a really interesting way of helping me understand what I did in my career and how it actually applied to digital twins. So I hope that's helpful. But what is the role of geography in a digital twin? Now, when I talk about geography, I do not mean human geography. I do not mean hammers and beards and cardigans with leather patches. I don't mean that. I don't mean what you might think of geography. I mean geography as a data management tool. If you understand where something is, then you can find out where other things are. You just saw it in what Sarah presented. If you know where the power station is or the pumping station is, you can see how they interconnect with each other. So if you understand location, you understand a lot more. Now, hopefully this will work. I just want to demonstrate the nature of spatial data and how it adds a dimension of space and a dimension of time to other types of information. This is a spreadsheet. It's in the world's most popular and favorite data science tool. It's satellite information, basically where a satellite has gone around the world, taken information, and it's built up a picture of fire and fire potential. And one of the columns you'll see there is called FRP, that's fire radiative power. And it's a measure of how much power has been emitted across a period of time by any piece of ground. And you can use that information, you can sort it. I'm just going to move this out of the way. Don't let me stand on that. You can sort this information, you can color code it as I've done over here. You can do things like, let me just get this up here properly. I'm actually going to make it a bit smaller so I can see the bottom of the screen. You can do things like look at the frequency of this data and map out the frequency. And you can do all sorts of analysis tools. But let's go back to that raw data and just look at we have a column called latitude and longitude. So I'm just going to select all this. Now latitude, obviously, this tells us the location of this data. So I'm going to select all of these, and then I'm going to make a pivot table. Insert and pivot. Say OK to that. I've practiced this a lot, so hopefully it works. Here we go. So, pivot table. First thing, latitude. What is latitude? It's how far north and south you are, how up and down. It's a little bit like a row. So let's take latitude and make it a row. What's longitude? It's how far east and west, left and right you are. So let's take that. It's a little bit like a column. What we want to measure is we want to measure the sum of the fire radiative power over time. So we put that into here. And I have a spreadsheet. Okay? Next thing I'm going to do is I'm going to take the row labels. And the earth starts, zeros at the top. It's the other way around. So I'm just going to order these. And I'm going to say Z to A. I've got a video of this in case it doesn't work as well. So. And then I'm going to select all my data. I'm going to take this thing and I'm going to make it 18 pixels, which is really hard here. And then I'm going to take this data and I'm going to take this in and I'm going to make it 18 pixels. There we go. And now, I don't know if you can see this, but if I take this data and I zoom out a little bit, you can start to see it looks familiar. Yeah? That spatial data makes it different. And let me just do a little bit further with this while I'm on a roll. So I'll take everything and I'm going to fill it, and I'm going to fill it with black. So we have a black page. And then I'm going to go and do conditional formatting. And I'm going to get color scales. I'm going to get more rules. I'm going to go for 3 color scales. I'm going to change them all to percentiles. You can tell how much I've practiced. Let's get our color scales. And then I'm going to make the lower percentile a nice sort of calming blue. The midpoint, I'm going to make a slightly alarming red. And the top, I'm going to make a fiery yellow. And say OK. And what we have now is what we call a thematic map, which shows us more than we had before, because I can now see that that data in that table is related to each other. The spatial dimension, the summing over time, brings this data alive in a way it couldn't do it before. Without this view, I could only analyze the data to a certain depth. You add location to things, and suddenly new things emerge, basically. And I can also take those locations and say, what else is in that place? What is the soil type there? What's happened to the rainfall over the last 20 years? What will the rainfall be like in the next 20 years? How will this change? I can do things I simply couldn't do if I modeled it without location. So hopefully that helps a little bit in what we're trying to do. So the role of geography in that, I'm glad I didn't need that video. First role of geography is to make digital twins better. Most digital twins model real-world things. Now, if you've got a model of like a capacitor and how it performs in its heat profile, it's not spatial inherently. But if you're modeling this, you're modeling cables. And the behavior of an electrical network comes from the properties of the cables themselves. And if you don't model them using shape, you've got a very poor digital twin. Now, this is, well, let's actually go try and demo this one as well. This is a digital twin. That equation up here is basically a growth model for a tree. So using this, I can go along time and go up and I can say, in 20 years, this is the volume of timber I have in this tree. And I can use this very simple digital twin to predict how a tree will behave. One tree, obviously. It's a very simple digital twin, and it's one factor. But if I do it 1,000,000 times, I've got a forest. And if I do it 1,000,000,000 times, I've got the UK. And if I then say to it, what happens if I plant more trees? How much more carbon? So volume of timber is how much carbon is stored, and so on. But I don't know which model of a tree. If that model of the tree was in an increased wind area, then it might look like that because it blows over. You're only going to get so far and the wind comes, and in the future there might be more growth. If this growth model is in Scotland rather than Cornwall, the tree might grow in a different way. I need location to make this into a proper digital twin. So one of the roles of location is simply to improve the digital twins that we have. The second part of it is, where's my slides gone? Not there. This is also the least smooth presentation you've seen today, but bear with me. The second use that I want to talk about is the natural environment. Digital twins model real-world systems. Those real-world systems live in our world. The spatial component of this provides the context in which they work. The natural environment is the environment in which they gain resources from and return products and waste to. Its capacity to absorb waste affects the systems we run with. We need to run digital twins in a context, which is our natural environment. And in the world of geospatial, you have got terrain models, soil models, vegetation models, river networks. You've got all this rich ecosystem of data that you can bring together to understand a digital twin in its context. And that's a very, very important thing. And there are a lot of people out there who produce this information, but they tend to be over in the geographic category and not in the engineering category. So GIS, mapping, location, spatial stuff provides a context within which all of these interconnected digital twins work. And then the last area I want to talk about is actual how it can help. This is what the area I think is most important, is how it can help us interconnect disparate digital twins. We're not talking about connecting self-similar systems in many cases. We're talking about linking water networks to electrical networks, to climate networks, to river networks, to flooding things, to people, and we have to understand all of that information. And location can act as a twin to link together disparate data sets. It is the index for those data sets. So let me just demonstrate this. We'll go to here. This is, does that come out okay on the screen? I think so. This is Edinburgh, where I live, or nearby there, and I've created a mocked-up electrical network. And this electrical network is a digital twin. It can do things like tell me where a cable can be connected to. And this network lives in a city which is full of people, and it's in a city where there's lots of competing needs. One need might be to take this network and extend it to cope with new development, or to add in renewable energy supply coming from wind turbines on Arthur's Seat in Edinburgh. So I need to plan out where I'm going to lay a cable, how it works, what load will be delivered to it. I need my electrical twin to do all the things that an electrical twin should do. However, in this area, there are listed buildings. In this area, there are trees that need to be protected. There's a map of reinstatement categories, which tells you if you dig up a road, what quality you have to restore that road to. The road digital twin of the surface of the roads is managed by Edinburgh City Council. The trees are managed by Edinburgh City Council. They have a digital twin of their trees, where they are, what species they are, how quickly they're growing, what their management type is. Scottish Gas manage the gas network, including abandoned gas mains. So the Scottish Natural Environmental Protection Agency manage a map of restricted areas for like scientific reasons and so on. In this area, there are multiple digital twins managed by multiple organizations for multiple reasons. And I need to understand my impact upon those and their constraints upon me. And I need to ask questions of all those twins. That's what we're here to sort of work on. So if I move my mouse around the screen, you can see these gray lines. Those gray lines are telling me the distance to the digital twin of the trees. So I can see what trees are here. It's telling me there's a listed building here. It's telling me contaminated land is down here. And these things here, they are abandoned gas mains. I'm gaining contextual information. I'm asking questions of multiple digital twins by simply taking the X and Y coordinate of my mouse and going to an API and saying, tell me about this place, please. Tell me what you need me to do if I put a cable in this place. That's what's happening when I move this mouse. It's a very simplistic, I'm just trying to get the principle across. Let me then go and create an actual cable. So I'm going to click here, and I'm going to start digitizing. And you can see I'm calculating the material cost of this cable as I go, and the construction cost. The construction cost is made by asking questions of the reinstatement categories. I'm going to an API and saying, if I put this line across the road network, how much will it cost me to reinstate that trench that I've dug? It's telling me a list of constraints when I go down over the gas network. Just by drawing a line on a map, I have linked 5 organizations together. I've interconnected 5 digital twins, and I've got a coherent picture. And I've just drawn a line. If I change the shape of that line, I change the question or the answer that I get from it. Now, this is not just a visual thing. Now this part, I haven't, it's only got, I'm going to turn the chart off. I am going to go here. This was written last week to get a point across. So over here, I have got a graph database. And if I go and just get rid of that line, and I start creating again, you will see, if I just put a line here, you can see there's a cable, and it's got a relationship with reinstatement categories, 2 of them. And I've now got a relationship with listed buildings, and I've got a relationship built up with abandoned gas mains. I'm building a structure of relationships simply by drawing this line, And that structure is a graph database that can be queried by an existing system. I'm building real relationships between systems. And if somebody comes in and changes a pipe's position, the relationships change. The interconnectivity emerges for free between these systems. And all I need is a knowledge of location, a reference system to put them within, and a way of talking between them. I need to understand the spatial component, when these things happen, and a way of talking, which in many cases is a group of experts working with APIs. That is what I need to start this process off. So that is my description of my own personal journey on this, and hopefully just raising the awareness a bit more of why geography, in terms of an information management approach, is so important, and why we need to take it more seriously, and why we need to use it in our daily lives, basically. And make sure that when we are planning out these systems, I can't find my last slide, it is there. Basically, we need to use geography better. That's all I'm trying to say. Thank you for your time.
Thank you so much. I've not seen anybody do so many alt-tab gymnastics all day, and you did it very well.
Thank you.
And you built it live. That was amazing. We do have some questions from the crowd. So number one up there is, how do you update your database with your urban design with real-time data? How do you use real data?
So it's a relatively, we use an API to stream data from a sensor, translate it, and just change it. It's a very simple process.
Just plug and play.
Yeah, in the geospatial community, there are many ways of doing that type of thing. It's very common. It's called SCADA in the utility space.
Yes. Yeah. Yes. Which standard do you use? No, that's not the question. So the next question is, how accurate should this data be in meters, question mark?
It very much depends on the use case. You know, it really does. So we're doing some work with the Dutch cadastre, the people who manage land parcels in the Netherlands, and by law they work down to a millimeter. Which,
oh, wow.
Yeah, it's impressive. In the UK we work to basically a meter or so. It just depends on the use case. Sometimes 50 meters is more than adequate, sometimes a few miles is adequate, and sometimes millimeters are required.
That's very fair. So I'm going to finish this off with one last question, because that would be fun. Is the first stage of a digital twin to specify the data required to solve the problem, or is it to spin up a drone and go capture a point cloud? That was a somewhat sarcastic question. I know, Miranda. Yeah.
I think both are equally valid. I'd say the first step in the digital twin is what do you want to do with it?
Yeah.
Which then leads on to how you're going to tackle that. And I think the maturity level helped me is that things don't have to be perfect on day one. You can work towards it.
And that's an excellent note to finish. Chris, thank you very much for that very interesting presentation.